All right. Welcome, everyone. Thank you for coming. How many of you are from London? All right. Well, thank you, and thank your city for the hospitality and the beautiful weather. I was a little worried. Like 7 degrees Celsius is the lowest we get all year in Israel, where I live. So this was a concern for me. But it's lovely outside, and thank you. And I'm very happy to be here for NDC again. So my name is Sasha. I work for an Israeli training and consulting company called Sela. And for the last 10, 11 years or so, I've been doing mostly performance and debugging work across a variety of application types, but .NET has always been my main focus. And Windows and Linux are the two places where I've been doing .NET performance work. And in this talk, which is slightly less technical than I'm used to giving, we'll talk about the whole performance investigation process. I want to share with you some of the things I've been doing, a couple of examples of what I call performance investigations, and hopefully you'll be able to come out of this talk with some ideas for how to actually do performance work in your own organization, and maybe some tools as well that could be useful. But this is all a bit higher level, and so if you're interested in more specific references and examples, I'd love to chat with you during the event. So again, the general plan is the strategy and tactics for performance investigations, mostly in the field, by which I mean as a consultant, I get called to different customers and magically expected to find or sometimes fix performance problems as well. So it's interesting and very challenging work, and there's really, I think, a few highlights that I can share from the whole process. So I want to talk about the performance investigation process in general, methods and anti-methods, a little bit of tools, and how to avoid getting lied to by some of the tools that you might be using. So let's start with the structure of a performance investigation. By the way, everything I'm talking about is kind of, like written in blood, but it's just my experience and the experience of other people on my team. So different practices might work for different people, and I'll be, again, delighted to if you could share your own experiences afterwards as well. So here's the structure of a performance investigation, how I usually prefer to conduct them. So first, obtain the problem description. And that sounds a lot easier than it is. If you have been doing performance work in your own organization, if you've been talking to customers and users at all, not just for performance issues, but in general, you know it's not always easy to extract the real problem description out of humans or systems also. So we'll talk a little about examples of what a good problem description looks like and what a totally non-actionable problem description looks like. Then what I like to do, especially when coming as an external consultant, is try and build a system diagram. Try and understand all the different interacting pieces. Now, if you're working in a single team or a single product, you might think it's a waste of time to build a system diagram when you start a performance investigation, because, I mean, you already have one, you have the design documents, you have the architecture blueprints for whatever system you have. A lot of times, though, especially when you're doing a new investigation, you discover that, the system implementation has slightly drifted away from the original design or from whatever you have documented on your internal wiki. And this is where building a diagram of the actual system as it is currently in production, and that's the thing you're currently investigating, is quite useful. Then I like to run a quick performance checklist. And what exactly to put on that checklist, we'll talk about this a little during the talk. But this just gives you a high-level overview of resource utilization across the system, how the different components are behaving, sort of lets you know which parts are okay and probably don't warrant additional attention, and which parts do really need a closer look and might be causing the problem you're looking at. And so this is where you hopefully are able to focus a little more closely on the specific area of the system that's worth further investigating. And then you investigate thoroughly. And this is like the vaguest step of the whole process. You investigate and you hopefully find the performance problem. You find the root cause, and I'll just spend a couple of seconds on that. By root cause, I mean the thing that actually fixes the problem in a way that will never have the same problem manifest again. So not just fixing the symptom by maybe scaling up the system or adding a little more memory, but actually finding the root cause that we can now eliminate and fix that problem for good. Now, some things are just naturally fixed by scaling up or adding memory, but often we tend to fix the symptom and not the actual problem. And then the problem really doesn't go away, and we end up spending more time on it in a week, and that's just a waste of for everybody's time. Then we fix the issue, we resolve the problem, and we verify that we have actually resolved it. It's now gone, and that's also something that people often forget. You know, we're all excited about just having found the problem and sort of found the 3 lines of configuration that have to be changed to fix it, and then we forget to make sure it really helped, and we go away, and then we have to come back in an hour and just go through the whole thing again. And finally, and this is super critical and important, and again, often forgotten, is to do a post-mortem. Document what you did, document the whole process, and I'll talk briefly about the post-mortem at the end of the talk and what should be on it. So this is the general structure, and let's start with problem descriptions and an example of a performance investigation that went quite terribly wrong and what was the cause of that. So a couple of examples of what I think are not so good problem descriptions. In this one, the customer complains that the application feels slow. Users can't really put their finger on it, but it's bad, might taking a look. Again, in your organization, if you are sort of the performance expert or the go-to person for performance issues, you might get this sort of thing often. As a consultant, I get this sort of thing often as well. It's highly unactionable. It's hard to understand what's going on. I don't know anything about your application or your system. What do you really expect me to do with this? Another example, which is also quite common, I think, again, in organizations as well as with external consultants, is we have a budget for fixing performance issues. So let's now use that budget because the year is coming to an end and we have that extra budget. Even if we don't use the budget for this year, we're not going to get the same budget for next year. So we just got to use the 2 days we have for finding and fixing performance problems. This is better than not investing at all in your performance problems, but it's not ideal. This is not the way it should work, right? You should factor in the performance work into the whole project lifecycle, and not just, when you have 2 days of budget left at the end of everything, just sort of try and see what you can do with these 2 days. But that also happens a lot, and of course, again, there is no guarantee that we will actually find and fix anything if we only have that little budget at the end. A couple of slightly better examples, I think. So this could be an email from like an automatic system, a template. And this says, so since 4:25 a.m., the 95th percentile latency to the front-end ASP.NET application increased to 1400 milliseconds. The previous value was 60 milliseconds, and this is consistent across geographies. Auto-scaling has kicked in and didn't help. Now, if you have an automated system that can generate this sort of email, that's like really awesome. Or it could have really been a human operator, but anyway, this tells you what's wrong, or at least it tells you the symptoms. It tells you what the person on the other side is expecting you to do. So let's say if we bring the latency back down to 60 milliseconds, you know they're going to be happy at least with this particular alert. And we know what mitigation steps were already attempted. So that also saves us a bit of time. Like, yeah, we tried scaling and it didn't help, so maybe the problem is somewhere else. Another example, which is less detailed, but I think is also quite good, and that's just a real example, just slightly reworded. In the latest version of the software, clicking from the patient details screen in some kind of medical software to the CT screen takes 11 seconds in certain hospitals. And this is unacceptable. It has to be under 2 seconds because our technicians, they don't have that sort of time to waste. So they can't wait 11 seconds for the CT screen to open. So this is something you've got to fix right now. So again, we know what the person on the other side of this email is expecting. They want this whole thing to take 2 seconds. It's now taking 11 seconds. Could be for a variety of reasons, but at least we know what the problem is. So having said all that about problem descriptions, let's take a look at an actual derivation of these values, of these problem descriptions, of the metrics that are getting violated in all of these cases. So this is like, imagine this conversation with a customer. It's rephrased from a really great blog post called How to Not Measure Latency, which I've linked at the end of the slides. So let's say we have this conversation with a customer or some other person on your team trying to figure out what the performance metric violations would look like for a system. So I ask, what are your latency requirements, dear customer? The customer says, we need an average response time of 20 milliseconds. Now let's assume for a moment this is like a web service, a web application. Let's say a web application that serves actual web pages to clients. So they're saying like 20 milliseconds response time. It sounds a little fast to me, but maybe like there's a reason for that. So I ask, what's the worst case requirement, and what is the reason that's your worst case requirement? The customer says, we don't have a worst case requirement, we just want it to be 20 milliseconds. Okay, so I'll go like, so some requests can be more than 5 minutes. You can still have an average of 20 milliseconds, but you can have some requests take more than 5 minutes. Well, of course not. Like, the worst case is really 100 milliseconds. That's something we can't, in no conditions, go over. Even if it's just 2 requests per day, right? So this is like bargaining for it. All right, fine. Nothing worse than 2 seconds. 2 seconds is really the furthest we can go. How often is a 500 millisecond response time acceptable? So for example, if you have 96% of your responses take 1 millisecond and 4% take 500 milliseconds, that works out, trust me, to 21 milliseconds average. So it sort of works out, and nothing is greater than 2 seconds. So is that an acceptable distribution of response times? And I mean, you can see where I'm going, right? I'm asking not just for a number that you just sort of pull out of thin air. I'm asking for a distribution which is actually based on what the customers are going to experience with this system. But it doesn't always end well, especially if you're not prepared to go through this whole routine. But what I'm saying is, what we need for monitoring, for alerting, for generating these problem descriptions is really more than just one made-up number like 20 milliseconds latency or 20 milliseconds average or 20% CPU usage across the system. So here's an example, like for a full-text query engine, we could say 90% of the queries should complete under 200 milliseconds, 99% under 600 milliseconds, and all the queries should complete under 2 seconds, and anything higher than 2 seconds, that's a timeout, it's an error, and I don't want to see that ever. So this is already better, and hopefully these numbers that this distribution is describing are not just made up in a vacuum, but they're based on actual users and business cases. So for some systems, it might be really hard to actually extract this information out of your users. Maybe you're going to need usability tests. Maybe you're going to need to talk to business people. What I'm saying is we as developers just can't make up these numbers, and operations people, they also can't make up these numbers. We have to get our alerting, we have to get our problem descriptions, we have to get the definition of what is a problem in general from an authoritative source, which is hopefully, again, tied to our business requirements. And once you have those metrics described as some kind of distribution, which we'll talk about a little later, then you want to monitor these things with some kind of dashboard, APM solution, cron job that runs in the background and gives you alerts. We'll talk about that a little in the rest of the talk. But again, for these problem descriptions to be actionable, for the numbers to make sense, for us to know what to fix and how often it's happening, we need to have thought about these metrics ahead of time. So let's take a look at a specific example of a performance investigation gone wrong. And to do that, I want to just talk briefly about 5 different anti-patterns for doing performance investigations, for things people do along the way for common mistakes. And you'll see some of them illustrated in my example. So the number one thing that usually goes wrong in a lot of my work is making assumptions. We're all very vulnerable to making assumptions about software, about the world in general. And so often we already know where the performance problem is before we even look at the system. Because it looks like the problem from last week, because it's John reporting the problem, and it's always the same thing when John is reporting the problem. We have some sort of guesses, and these assumptions can lead to a colossal waste of time. And again, I'll talk about a specific example coming up. Trusting instincts and irrational beliefs is sometimes even worse than making assumptions. Assumptions, at least you can sort of contradict, but irrational beliefs, they are really hard to fight. And by rational beliefs, I mean things like the storage system is never at fault, it's never the problem with the storage system, or it's just that the cellular connection is so slow in India that we should all just ignore performance issues coming from cell users in India. So these sort of rational beliefs or instincts that we might have about software are, again, considered extremely harmful. And a couple of additional examples. Looking under the streetlight is something I'll illustrate as well. And what I mean by that is looking where it's convenient for you to look, so where you have observability into the system. If you only have observability into a specific area, it's completely natural to jump to that area first and start investigating that, because you simply don't have the tools or the knowledge right now to investigate other things. So that's also a natural thing to do, but it could be, again, it could lead to a huge waste of time. And there's some additional examples which I'll illustrate later. So let's see a specific case, how I failed to diagnose a performance issue. I'm not super proud of this, but it is a good case study, I think, of things that can go wrong on a performance investigation. So here I am sharing this personal failure with you. So what we had is a document management system with several thousand internal users inside a specific organization. And it was basically a document management system, right? So you could load documents from some sort of network storage, you could modify them, save them, conflict management, all the sorts of things that come with document storage. And the network storage itself was a NetApp system accessed through SMB, through file shares. And this is like the general, very, very simplified architecture of this system. So you have clients connecting through WCF to an application server. And the application server is talking directly through a file share to a NetApp storage appliance, which is hosted on the same network. So it's all a fairly tight and closed internal network, not over the internet or anything. Now, some parts of this system I could investigate fairly easily, and I had the knowledge and the tools to do so. But some parts, like specifically the NetApp storage appliance, I simply couldn't physically access at all. And that's a pretty common theme, I think, with storage appliances. They tend to be those black boxes that you're not really allowed to access and investigate directly. And sort of it led our investigation a certain way, at least in the beginning. Suspecting the application server, suspecting the clients were causing the performance problem. Now, what was the performance problem anyway? It was actually a little hard to describe, but we managed to narrow it down to certain operations on certain documents leading to timeouts. So it wasn't immediately visible with like an error message or anything, but we could figure out that the subsequent problems were caused by a timeout in some load and save operations. All right. So here's how it starts. We processed a lot of network traces, trying to figure out where the timeouts might be coming from. And I was able to see that the mean latency to storage from the application server, going back to the previous slide, from the application server to the NetApp storage appliance, the mean latency, the average latency was 11 milliseconds, but we observed peak values of up to 1,200 milliseconds, so over a second. And that could potentially lead to the timeouts people were describing. So we had to look at some information from the storage appliance itself and the storage latency counters. So we did have to look at that black box on the right. All right, so a couple of days later, we got some information from network engineers looking at that NetApp storage appliance. And the network engineer says, his name was Network McNetwork. So he says, if I'm not mistaken, the network latency maximum was 10 milliseconds with an average of less than 1 millisecond. Now, this was computed by looking at the network ingress point on the storage appliance itself, but discounting the actual storage disk accesses. So now we have the full latency of 1,200 milliseconds to storage, and we have the specific part of that which is network related, and that seems to be 10 milliseconds only. So that leaves 1,190 milliseconds unaccounted for, and we suspect they are in that storage subsystem. All right, so the NetApp consultant, who is the only person in the world equipped to monitor and diagnose issues with NetApp storage appliances, he will be in next week. But the system administrator we have who is in charge of that storage appliance says there's no way the NetApp latency is greater than 5 microseconds. Now 5 microseconds for all disk accesses sounds really optimistic to me, but I don't know much about NetApp appliances, so I just had to trust them until the NetApp consultant came in. Then he came in, and he said, it's actually 5 milliseconds and not 5 microseconds, but that's almost the same thing. And in any case, it's not the storage system in anyway, because it's nowhere near the latency that you're describing that might have caused the timeouts. We're talking about 5 milliseconds only. And then I asked, is that the average or the peak value, the 5 milliseconds? Because I already know that the average time for loading and storing documents is pretty fast anyway. It's like 10, 11 milliseconds across the board. But we do have those rare outliers which are over a second. So when you tell me that the storage appliance is 5 microseconds, 5 milliseconds, whatever, is that the average latency for saving or storing documents, or is that the worst case? And then we got the following reply. It's the maximum average value over 60-second intervals. I love this. I gave this presentation a couple of times, and I still don't understand what this means. And to this day, we don't know what exactly it means, because we got a lot of conflicting answers when we tried to press it. So that's what we got. Again, maximum average value over 60-second intervals. Now, what could it be, right? So maybe we take the average value over 60 seconds. So we aggregate for 60 seconds all the latencies of storage accesses. We get the average value of that. And then we take lots of these 60-second intervals and we gather the maximum of all these averages. That's one option. Maybe we get the maximum over each 60-second interval, and then we do an average of the maximum values. That's another option. Maybe it's something else entirely. We just don't really know. And it's not because it was all done over email. We actually had a few phone conversations about this as well, and we still don't know exactly what was meant here by the maximum average value over. So yeah, it is probably a communication failure. Of course it is. Thank you. But yeah, that's where we were. And then I, again, not being a NetApp expert really, I tried to look up online if there is a way to maybe monitor the storage system a bit more closely. And I found that NetApp actually, unsurprisingly, has performance counters that you can enable over SSH and just read them whenever you want, right? And these include the average read and write latency, and that's in milliseconds. And that's gathered every second. So you can get every second the average read and write latency for the NetApp appliance. It's not exactly what I wanted, but at least it was updated every second. Unfortunately, we ran out of budget for the NetApp consultant at this point. Turns out they're really, really expensive. He had a bag that said NetApp all over it. It's a very expensive bag as well. So at this point, the investigation just ended. And a few months later, I actually heard back from that customer. And they were able to work around the problem, not by replacing the storage appliance or by figuring out why the storage maybe was slower than expected, but by retrying automatically in the client, like under the covers, by hooking some APIs and just injecting retries until it worked. And it meant deploying additional code to every single workstation and doing that work on the client. But hey, it did solve the issue. They never ran into these timeouts ever again. So I consider this a serious failure from a lot of aspects, right? So there were assumptions made, a lot of irrational beliefs along the way, communication failures during this entire investigation. The whole budget problem was a problem. So these are some of the things that could go wrong. And I think hearing this story sort of gives you an idea of what to expect. I have another story coming up, which is a little more optimistic, but that sort of thing definitely happens and will happen to me again. And after all that, we talked to the NetApp guy again, and he said again, you know, I understand that you did this workaround and it's all working fine now, but I mean, I'm telling you, there is no way it could have been more than 5 milliseconds, because that's how NetApp works. There is no way for NetApp to actually work slower than 5 milliseconds. This is the sad ending of this story. All right, so we talked a bit about some of the things that can go wrong in a performance investigation. I want to touch really briefly on the other 3 things: look under the streetlight, random tools, and blame the tools. So here's an example of looking under the streetlight. If you have a bunch of expensive tools that give you observability into a certain part of your system, you might be just using these tools automatically for every problem you now have. And a classic example of that is CPU profilers. CPU profilers are really abundant, and they're not really hard to use. And this is an example of output from the Visual Studio CPU profiler. It's really easy to run and get results from an application. And in this case, we run it on a web crawler, which is like downloading pages off the web as fast as it can. And the profiler results point to a particular function called console.writeLine, which is taking 66% of the application's CPU time. Well, does that mean we have to fix console writeLine or maybe replace our usage of console writeLine with some other more efficient method? Not necessarily, because maybe our application is not really taking lots of CPU anyway. And if we run a CPU profiler, we're looking into only that particular component, only that particular resource, which is the CPU. And we are ignoring time spent doing I/O, network requests, and all other kind of activity. So this, again, is an example of using a tool that gives you observability into a specific area of the system because that's easy, or because you paid a lot of money for a license for that specific tool. And it gives you some results, but they're not necessarily the results that can help resolve the issue you have. Another example of this is sort of not trusting your tools, or maybe misunderstanding your tools. This is a really simple example of a console application I wrote, which runs for 2 seconds and then throws an out-of-memory exception. But then you look in Task Manager, and in Task Manager you look at the memory column, and it says the application is only using like 10 megabytes of memory. So could it be that the .NET runtime is so bad that you can't allocate more than 10 megabytes of memory before it runs out of memory and throws an out-of-memory exception? Or maybe Task Manager is just lying to you and like misrepresenting the memory usage of that application. There's a lot of theories that you could have at this point, unless you know already what's going on. And what's going on is that the memory column in Task Manager only represents part of your application's memory usage. Specifically, by default, Task Manager shows the private working set, which is memory not shared with other processes, and memory which is resident in physical memory, which is sitting in RAM and not possibly paged out. So this is just part of the application's memory usage, and that could be why we still run into an out-of-memory exception, even though the private working set is so tiny. So it's just about misunderstanding what the tool is saying, or maybe not exactly aligning what the tool is saying with our model of how the application or the system works. And another example of a pretty common problem is just sort of throwing away the tool completely. And here's a classic example of that. So I ran Notepad, and then I attached a really popular sysinternals tool called VMMap. VMMap, if you haven't used it, it's really super cool. You attach it to a process, and it tells you exactly a breakdown of that process's memory usage. So how much managed memory is there, how much memory is used by the heap, by the stack, by loaded DLLs. It just breaks down the whole thing into components. And then, like VMMap says about Notepad, that Notepad's total memory usage is 2-point-something terabytes. And I mean, it's Notepad, and I haven't even opened the file. It's just plain blank Notepad. So that couldn't possibly be right. It means VMMap is lying to us. Maybe it wasn't updated for the latest version of Windows. Maybe there's a bug in Notepad. Maybe there's a hacker attacking our system. So in that sort of case, you might just discard the tool completely, throw it away, and never use it again. But actually, VMMap is telling the truth. On newer versions of Windows, there is a security feature called Control Flow Guard, which leads to 2 terabytes of memory being reserved in each process if it opts into that security feature. And this is just reserved virtual memory. It's not actual memory that you're paying for. It's not disk space. It's not physical memory. It's basically nothing. It's just a reserved memory space which is used by that particular security feature. So every process will have 2 terabytes of memory if you look at reserved memory as part of your memory. So it's not lying to you via map, it's reporting the truth, but you have to understand what it's saying. And maybe, just maybe, you have to trust the tool first and try to understand what the tool is reporting. But I will have, in just a couple of slides, an example where you shouldn't trust the tools. So it really goes both ways sometimes. So these are, again, some of the common mistakes people make when conducting a performance investigation. I say people, but I do that as well. I mean, these are all very natural things to do. Trusting instincts, irrational beliefs, making assumptions, using tools because you've used these tools before or because they're handy and give you observability into a certain part of the system. So let's talk about a method which is slightly more rigorous. It's not a lot harder, but it works well in a lot of cases. I haven't invented it. It was popularized by Brendan Gregg, who's a performance architect working at Netflix today, and it's called the USE method. And USE stands for utilization, saturation, and errors. I'll talk about each of these in a moment, and then I'll tell you what the method is. So utilization, I guess, is the easiest metric to define. It's a metric of load, which proportion of time a particular resource in your system is working, as opposed to the time it is idle and not doing anything. For different resources, you could define the utilization slightly differently, but that's the obvious metric of load or usage utilization. So for a CPU, it's the proportion of time the CPU is busy executing instructions. For a web application, could be the proportion of time the application is actually servicing requests and not just waiting for additional requests, and so on. Saturation is a metric of overload, how overloaded or queued up that resource is. So if you have work waiting for that resource to become available, then you have saturation. For example, for a web application, if you have web requests, HTTP requests sitting in a queue and not getting processed immediately, then you have saturation in your web server. If for a disk drive, if you have requests, writes or reads, waiting for the disk to start servicing them because the disk is busy doing other things, then you have saturation for your disk, and so on. And finally, errors are just that. Errors, exceptions, failures, faults, whatever you call them. So for each of the resources in your system, hardware resources as well as software resources, you want to look at utilization, saturation, and errors, model these things, measure them, look at them for each of the resources in your system to understand what's going on. And this is the initial checklist stage of your investigation. You haven't done any thorough analysis yet. You're just getting a reading of how the system is behaving. And it might sound completely trivial, and you're already doing it, and you have wonderful tools and dashboards that give you all this information. But if not, then you absolutely have to start there. If you don't have that visibility into each of the things you have in your system, then you have a problem whenever you perform a performance investigation. You will not know what to look at. You will not know which potential black box could be causing problems for the rest of the system. So just a couple of examples. For hardware resources, this is like a typical workstation. You have a CPU, you have a disk drive, you have a network card, you have physical memory, you have a graphics card attached as well. For each of these things, and for the buses, for the interconnects between these things, you can look at utilization, saturation, and errors. I've given a couple of examples, but for hardware, they should be relatively easy to derive, and they should be also relatively easy to monitor because, I mean, most hardware is just generally the same. So CPUs are CPUs, and we have pretty standard tools for monitoring CPU utilization or CPU saturation. But software, software is a whole zoo of different frameworks and components, but we can do it for software as well. We can identify the software resources in our system, web servers, load balancers, backends, databases, caches, and so on. And for each of these things, we can look at utilization, saturation, and errors as well. And for software, if it's well-designed software and monitoring is part of the whole thing, the whole framework you're buying, then you'd be able to easily monitor these metrics for that particular software. If it's not that well designed, it might be really hard to extract USE information out of a component. So this is, again, something that obviously depends on the specific pieces that you're using to build your system, but you should have that sort of visibility into them as well. Now, I've given here on the slides, just for reference, a USE checklist for some of the hardware resources on Windows systems. It's just an example, and you can find this sort of thing on the web. These are just various performance counters that give you for network cards, for disks, for CPU, for memory, the USE metrics which you can easily monitor. I'll give you the whole set of slides so you don't have to take photos of the checklist now. And you can automate the process of collecting this checklist and getting alerts based on that checklist. Just a couple of very basic rudimentary tools if you don't have anything super fancy to monitor your system. Typeperf is a command line tool built into Windows which can generate CSVs of these different metrics on the console. And perfmon is the Windows performance monitor which can collect performance information for you in the background, and it can even issue alerts. It can, for example, run some sort of application when one of the metrics is breached. And of course, there's plenty of third-party agents that will collect this information for you, and many of them are already tuned to collect the USE metrics already. So once we have that kind of high-level set of things about our system, we can perform a performance investigation more easily. And I want to show you one example where we really didn't need a lot of information to diagnose the problem, but we did have access to metrics, we did have access to the system, and that helped solve the problem at the end. So this is a story of how I found a bug in the CLR 2.0 garbage collector. And that sounds like really unlikely, a bug in the garbage collector. When they do happen once in a while, before we blame the garbage collector, we do have to, make sure, exonerate every other piece of the system. But in this case, it really was the garbage collector. This is from 9 years ago, 8.5. So it's not a super brand new story. And 8.5 years ago, we didn't have access to the CLR source code. So that was a little harder to diagnose than it might have been today. Anyway, the symptom was we had a packet processing system getting requests off the wire and doing some kind of processing before just throwing the packet away or recording it to a file. And sometimes when processing a very specific kind of packets, we had hiccups in the application. So it would drop thousands of packets before proceeding to operate normally, sometimes for hours at the end. So it would just work for a few hours, and then it would have a hiccup of a couple of seconds and just keep working normally for a few more hours. In the logs, it looked like this. So it would just work normally, and then boom, we have a 500 millisecond pause where nothing is happening, even with the highest, with all the logs turned on, nothing would be printed, just 500 milliseconds of doing nothing. Now, if you've been doing some investigations that involve the garbage collector, you might immediately suspect this has to do with GC pauses. So the GC is stopping your application in order to clean up memory, and this is why you're having these pauses. It's not a bug in the garbage collector, Sasha. You're just not understanding how the garbage collector works. So that could be the case, but let's keep talking. So this is what it looked like when we collected a bit of performance information. You can see two metrics here. The blue one is the number of packets processed per millisecond. So we were processing tens of thousands of packets per second, or tens of packets per millisecond. And the red line is CPU utilization across the system. And then you can see at timestamp 3000, something weird happens. We have CPU usage drop, but not completely, drop to about 20%. And we have packet rates drop, again, not completely to zero, but very close to that. And then, after a little time, we have CPU spike up to 100%, and packet rates drop to zero. So this is complete zero, no packets are being processed over here. And then it all goes back to normal, slightly more jittery because there's some packets to make up for, but generally it goes back to normal, and it could go for hours on end like this. Okay, so again, to make a long story short, another funny thing that we were able to observe after a while is that these delays during which no packets are being processed were always multiples of 250 milliseconds. So it was like 252 milliseconds, 503 milliseconds, 751 milliseconds. It's almost as if someone had some kind of timer or a sleep statement for 200 milliseconds, which was getting hit somewhere inside the system. So we kept investigating, and eventually, and again, it's 9 years ago, it was a bit harder back then, eventually we were able to get a thread dump of what the system was actually doing during one of these hiccups, during one of these delays. And then what we discovered is we had 4 garbage collector threads, and they were just sitting there waiting. They were not doing a garbage collection yet. They were sitting there waiting for a garbage collection to start. And then we had 2 application threads. One thread was parsing packets just as fast as it could, and another thread was starting a garbage collection. So another thread was trying to allocate memory, and it couldn't, and it hit a GC, and what it's trying to do right now, it's trying to suspend this other thread. It hasn't succeeded yet. It didn't suspend the thread because the GC threads are not working yet. It's just trying to stop this other thread on the left. And it's trying really hard. And it's trying really hard for 500 milliseconds and 750 milliseconds and so on, sometimes all the way up to 1.5 seconds, just trying to suspend that other thread. And that looked really suspicious to us. So we started reverse engineering that suspend function and relevant code around it. Today, we would just look up on GitHub at the CLR sources. But back then, we reversed it a bit and found the following loop in there. And again, cutting a long story short, there was actually a 250 millisecond timeout in there. So basically, it goes something like, as long as we haven't successfully suspended the thread and we haven't given up yet, wait for 250 milliseconds to see if that thread was successfully suspended. And if not, then sometimes it would retry, and sometimes it would jump out of the loop and just do an aggressive suspension, which doesn't require cooperation from that other thread. So this whole thing eventually looks like a bug because we're not supposed to be stuck in this whole suspension process for so long, but I didn't know it back then. I couldn't create a pull request, so I think I submitted an item on Connect, and I wrote a blog post about it, just see if someone else has ever run into this sort of thing. And then a couple of weeks later, I got a comment on my blog post from Maoni Stevens, who's the lead developer on the garbage collector at Microsoft. She's still at that role today. And she wrote, I ran your repro, and I do see the suspension problem. We'll look at that and see what happens. And they found a bug in the garbage collector, which was responsible for that suspension problem, and they fixed it eventually, and so if you're interested in the whole story, you can read it on my blog. But this is an example of where we didn't make anything, we didn't use any super fancy tools or techniques, we just sort of methodically narrowed it down a little more and a little more and a little more until we were able to figure out it's not really our fault at the end. We did manage to find a workaround as well. It's all on my blog if you're interested. So this is an example that I'm a little more proud of than the previous story with the NetApp appliance. So now that we talked about the performance investigation process itself, I do want to leave you with some practical things as well. So I want to touch briefly on good performance tools, what good performance tools look like. And again, it's not a very hardcore session, so I'm not going to be showing you demos of performance tools, but I do want to sort of touch on what kind of tools are out there and which tools work well. So I think there are 3 kinds of performance tools all in all. The first is counting tools, which only tell you how often something is happening. And these are the cheapest tools usually in terms of overhead. They don't have a lot of overhead, they're just counting something. So they're telling you the number of requests your application is able to process, or the number of packets sent over a particular network interface, that sort of thing. Then we have latency tools, which tell you how long something is taking. And that's usually a bit more expensive to collect because you have to record a timestamp at the start and the end of a certain operation, and you have to aggregate this information. The output of this sort of tool, of a latency tool, could be not just the average value, which is not really great, but could be something a little better like a distribution, a histogram, a range of values, a range of latencies that you can then investigate. And finally, the deepest tools will tell you what is causing something to happen across your system. I call those the stack collection tools. they will give you call stacks of interesting events like disk accesses, garbage collections, memory allocations, and it would be able to look at these stacks, look at these stack traces, and aggregate them. And this is usually the most expensive things because collecting stack traces, aggregating them, and so on, that's a rather expensive operation. All right, so these are the types of tools, and I'll mention a couple of examples, but here are some of the qualities I want these tools to have. And again, it might sound a little trivial, but not all tools are really great at these things. So first, low overhead. I'll touch on that in a moment, but if you're running a performance tool, especially on a production system, you don't want it to slow things down too badly. You want the tool to be accurate. Again, it sounds kind of obvious, but not all performance tools really are that accurate, or they could be skewed by what your system is doing or what your application is doing. You want your tools to have a quick turnaround, so you don't have to wait for 8 hours to get results out of a performance tool when you're under pressure to do a performance investigation. You want the tools to be production ready, by which I mean you can actually put them on a production system and run them over there without any additional extra preparation or any invasive steps like restarting the system. And finally, I want the output from the tool to be easily focusable so that I can find interesting things in the output right away without having to read through, say, 50 pages of reports to find what's causing my problem. So let's talk about some of these aspects for a bit. Let's talk about accuracy first. A lot of the Java profilers, and I know it's a surprising twist, but I never said it's going to be a talk only about .NET performance tools. So a lot of Java profilers actually produce blatantly irrelevant results, completely irrelevant or false results when you use them for CPU profiling. And it's a result of using a documented API which collects stack traces of threads when you want to see what your threads are doing, which sounds like a totally legit thing to do. You want to stop threads, look what the thread is doing, collect the stack trace, let the thread keep running. It's useful to do a performance investigation or to profile the thread. Unfortunately, the way that API works, the way it captures the stack trace of a thread is completely biased because it doesn't capture the stack trace right away. It waits for the thread to reach a safe point. And I'm not going to explain exactly what a safe point is, but the thread could be running for a while until it reaches the next safe point. So if you ask, what is this thread doing, you're not getting the right response right away. You will know what the thread will be doing when it hits the safe point. That's the result you're going to eventually get. And sometimes it completely skews the results. And there's actually a research paper on it called Evaluating the Accuracy of Java Profilers. I recommend it. It's really funny. And one thing it shows on the left here is that they ran 4 different profilers on the same workload exactly, and each profiler thought some other method was running longest. And they also disagreed on what longest means. So some profilers thought the slowest method was taking 5% of the time. Other tools thought it was up to 20% of the time. So they not only disagreed about which method was the most expensive one, they also disagreed what most expensive is for this workload. Again, it's exactly the same application, just 4 different tools. And that means like someone is lying. Maybe all of them are lying. Maybe just one of them is giving the right results. But this is highly suspicious. So what I'm saying is that unfortunately, in some cases, yes, the tools do lie. And if you're using a new performance tool and you don't understand how the performance tool works, then you sort of have to sanity test your profiler. You have to see if it makes sense, the results you're getting, if they make sense on a known workload where you know what results should be generated, and see if the profiler actually generates that result. Now on Windows, for .NET applications and for other kinds of applications on Windows, we have a really great system for doing profiling and performance collection, which is called ETW, Event Tracing for Windows. And we could do a whole different talk just focusing on ETW itself. And it's a really great facility because you can enable it without touching the target process. You can collect a lot of information. It's all really wonderful and useful. So again, a completely different talk on the merits of ETW, but I just want to focus on one aspect of it when talking about tools, and that's quick turnaround, getting quick results out of the tool. So this is an example of a performance session where I collected information from ETW using a performance tool called PerfView, and this is what the log looks like. So first it says, collecting information for 10 seconds. and that generates 15 megabytes of data. So that's already a bit suspicious. It means if I collect for hours or days on end, I'm going to get really huge log files. But OK, let's leave that for a moment. So collected for 10 seconds, and then I stopped collecting information. And it took 12.7 seconds to do something called the CLR rundown. I don't know what it is. Well, I do know, but you don't have to know. You don't care what it is. And that took 12.7 seconds to complete. Like, this is not part of what I was measuring. It's just extra time spent at the end of the profiling session. And then it took 4 seconds to do some kind of conversion. Again, I don't care what sort of conversion it was. It took another 4 seconds of my life. And then another 4 seconds opening some file, and another 0.2 seconds opening the same file. Interesting. So all in all, it took like 20 seconds to open the file from a 10-second performance investigation. This is what I mean by quick turnaround. This is not quick turnaround. If I have to spend twice as much waiting for the results as collecting the data in the first place, that's not quick turnaround. So I'm not saying I have the perfect solution, but I do want to tell you about a couple of tools I built which have which are helping me anyway address this problem at least a little bit. And these are eTrace, which is a command line tool for monitoring ETW events, which works in real time. So you can run it and get real-time printouts when ETW events occur. And it looks something like this. So you can run it, and then you get, in real time, you get printouts on your terminal with the event you care about. For example, on the top, I'm collecting garbage collection events. So whenever a GC occurs, I want to know about it. On the bottom, I'm collecting allocation events. So when a certain threshold is breached, I want to know that a process is allocating lots of memory. Again, just examples, but by having that printed in real time, I can do long-term performance collection and not wait for the whole thing to complete before I can view the results. And that's really valuable when you're not just measuring a 10-second workload. And another tool is called Live Stacks. And this is, again, a real-time tool which collects stack traces of interesting events and prints them out to the terminal as well. So you can use this to do real-time profiling. So you can profile what the process is doing and just get a dump every 5 seconds with the hottest methods, what the process is doing right now. You can use it to profile disk accesses, garbage collections, lots of other events. It's all based on ETW again. And the results are kind of ugly. It's just a bunch of stack traces printed to the terminal. But they can be visualized. You can take the output from live stacks. Here's another example. You can take this text output, and you can visualize it, for example, using flame graphs, which, again, we could spend a whole session talking just about the benefits of flame graphs. But this is one way of visualizing stack traces, visualizing lots and lots of stack traces in a format that allows easy drill down and focusing on whatever you care about. So if you haven't seen flame graphs before, it's perfectly fine, but you might want to consider looking into them. So just wanted to talk to you briefly about, again, some benefits of tools with a quick turnaround, with a low overhead, with, of course, accuracy hopefully is a feature that these tools have as well. And one final thing I have 7 minutes and 22 seconds for is a quick rant on statistics. And I have nothing against statistics. Statistics is a beautiful thing and a beautiful field, but the way we sometimes use statistics, the way we use output from performance tools is often, again, leading us up a completely wrong alley, and that's what I want to talk about briefly. So averages, like we already saw, are often quite meaningless for understanding what's really happening in your application, for understanding if your system is really experiencing a performance problem. So some people use medians instead. They're not a lot better for understanding the whole range of values, because you can't really reliably take lots of values and accurately represent them with just one number. It's impossible. And so any attempt to do that sort of thing without really looking at the whole range is sort of doomed to fail. Percentiles are one common way of addressing this problem, trying to visualize a range of numbers, a distribution of numbers, and we'll talk about them in a moment. And finally, visualizations for all this stuff are really important for trying to understand the actual values. So let's see a couple of examples. The average response time of my application is 29 milliseconds. Is it good? Is it bad? Does it mean anything? Suppose we do have the context and we understand what kind of application it is and what we're talking about. Is it good? Is it bad? So here's a distribution of values which has an average of 29 milliseconds. I know you can't see all the tiny labels, but this distribution looks like it's really close to the average. The average is this blue line over here. So most of the values are clustered around the average, and it's perfectly nice and pretty. This distribution also has an average of 29 milliseconds, and then the average is over here. This is 29 milliseconds. We have a lot of values clustered close to that average, but they're really smaller than the average. But we have this additional cluster of values which are almost 10 times bigger than the average, and they can't be discarded. Because this could be the set of users having a problem. This could be the set of problematic requests. This could be the timeouts in my document storage system. We can't just say the average is 29 milliseconds, so these things do not exist. And it's very common in performance monitoring that you would have this sort of second mode of values for latencies and for other metrics as well. It's pretty common that you would have the normal values and you would have some kind of cluster of problems over there. This is a really cool paper from Autodesk written last year which focuses on visualization, and all these different dots you see on the screen, they have the same average across the x-axis, the same average across the y-axis, and the same standard deviation as well on the x-axis and the y-axis. And even the same correlation between the x's and the y's. Even the dinosaur, which showed up at some point, even the dinosaur has the same average across the x's and the y's as all the other sets of dots. So what I'm saying is, and what these researchers are saying as well, is that without seeing the actual shape, you can't say a lot about the values just by looking at the average or by looking at the standard deviation. So visualizations are really important in general and for us humans specifically for understanding information at a glance. Here's another example of what I think is not a great way to present performance information. This is output from benchmark.net. Hopefully some of you have seen it or used it. It's an amazing benchmarking library for .NET, an open source project. And benchmark.net reports results at the end somewhat like this. It prints out the average and the standard deviation, as well as a bunch of really interesting statistical information like skewness and also kurtosis. Yep, I don't know what it is, but it does report this. And also confidence intervals and a lot of other beautiful things. But one thing that's missing, in my opinion, is just a visualization of what the numbers look like, what the numbers for that benchmark actually looked like. And there is a way of getting this information out of benchmark.net, but it's not on by default. So if you run this thing by default, you only get the numbers. You don't see the results. You don't see the distribution. And what's even slightly worse is that benchmark.net, because it's a benchmarking library, so it's maybe a bit more acceptable, it actually throws away the outliers. It throws away the unlikely results. So in this example, I know it's a little hard to see here because of the light bleeding into the projector, but we had 52 results from the benchmark, and 11 of them were removed because they were considered outliers. So, not even just 1 or 2, but 11 out of 52 results were removed from the statistics because they would screw up the values. So we just removed them, we got rid of them. It's not a great thing to do if you're looking at actual performance numbers from a production system, because the outliers, the hiccups, those weird lines breaking out of all the charts, these are the problems, these are the things you are investigating, these are the things possibly causing problems for your users. Now, just one final thought. If you look at this sort of diagram, so this sort of visualization, you can obviously see the outliers. You can also see the 99th percentile, which is over here, and the 99.9 percentile, which is over here. And you might ask, should I really even care about these super outliers, about these super hiccups, which are completely off the charts? Like, is it even likely that a user would ever hit this sort of behavior in their whole lifetime? So, yeah, that's how you can visualize this stuff, but I'll just jump straight up to who cares about the 99th percentile. So I did a little experiment. and I opened up my browser developer tools, and I went to Amazon.com, and I saw that the Amazon.com webpage made 328 requests. And so let's assume for a moment these are all completely independent and they all have the same latency behavior. What is the likelihood that you would see the 99th percentile? It is actually 96%. So if you make a lot of requests, you will hit the 99th percentile pretty often. And so if you have operations in your system that the users are performing again and again, if you have certain behaviors that cause lots of requests, then you should care about the 99th and 99.9th percentile because they're not as unlikely as we think, just looking at the dashboards behind the scenes. So there's just a parting thought about Statistical. So wrapping up, this is the final thing I want you to think about. At the end of a performance investigation, conducting a post-mortem is something I've mentioned at the very beginning is quite important. A few things I like to put on the post-mortem is what we did, what the steps we took were, what was effective and what was not, which tools would be useful for diagnosing this problem in the future, which tools that we didn't have would be useful and how we can maybe build them. And one thing to think about finally, can we somehow manage to maybe in the future just diagnose this sort of problem automatically? Can we remove the humans from the equation? Can we diagnose problems and just resolve them without any human intervention? So automating ourselves out of a job. So we've talked about what a performance investigation looks like, some methods and anti-patterns. I'm 30 seconds behind, so I'll just leave you with a link to the slides. If you have any questions, I'll step up the stage real quick, and I'd love to chat with you. I'm here today, I'm here tomorrow as well. Thank you very much for coming. Thanks.